So first of all, I'd like to thank the organizers for giving me the opportunity to speak. And I'd also like to thank you for joining me as an audience member in this virtual setting. So today I want to tell you a little bit about some recent work that I've done on trying to understand arithmeticity of manifolds via their sort of geodesic geometry, so their geodesic submanifolds. And everything that I say today is going to be joint with Uri Botter, David Fisher, and Matthew Stover. Um, Okay, so for today, I want to focus on a specific class of hyperbolic manifolds, and that's going to be the finite volume hyperbolic manifolds. And specifically, I want to assume that the dimension of them is at least three. So three manifolds are great, but it turns out that for everything I say, it's not going to be true for surfaces. And anytime you see me use gamma in this talk, it's going to be the corresponding fundamental group. So this is some lattice in the isometry group of hyperbolic space. And when I'm talking about hyperbolic space, at least until the very end of the talk, I mean real hyperbolic space. Okay, so what are some examples? So at least in dimension three, a particularly nice example is given by the Bianchi groups. So these are PSL2 of some ring of integers in an imaginary quadratic field. If that's not your kind of thing, then you can just think about maybe the Gaussian integers. So Z adjoint I, it's a perfectly good example. And here the isometry group of orientation preserving of hyperbolic three space is PSL2C. So this is a perfectly nice discrete subgroup that when you quotient hyperbolic three space by it, it gives you a finite volume hyperbolic manifold. Some other examples are going to be knot complements, for instance, as long as your knot isn't too trivial. So if you take a three sphere and you remove a knot, say the figure 8 knot or something like this, then you'll get a nice finite volume hyperbolic manifold. And you can also take your favorite mapping torus of a pseudo-Anosov mapping class. So by a theorem of Ian Agel, in fact, manifolds of this form finitely cover every finite volume hyperbolic manifold. So up to commensurability, I mean, most of them look like, or I mean, up to commensurability, they all look like this. So these are some fairly nice geometric constructions of manifolds. And in 2 and 3 dimensions, via say Teichmüller theory or mapping tori or knot theory, there are a lot of nice geometric constructions of hyperbolic manifolds. It turns out that in dimension greater than 3, it's a little bit trickier to start to find manifolds. So I think like the first known construction of manifolds that worked in arbitrary dimensions, so all dimensions bigger than 3, are arithmetic manifolds. And whereas I'm not going to define an arithmetic manifold in this talk, I urge the interested audience member to, if they want to see some explicit constructions, go check out Michelle Chu's talk. I think she actually gives some explicit constructions. So arithmetic manifolds have been known for a long time, and there's some sort of number theoretic input that allows you to construct hyperbolic manifolds in all dimensions via this. There's also an abundance of non-arithmetic manifolds as well, and you can use sort of cut and paste techniques to build non-arithmetic manifolds. So here I have some little diagram. So here on the left, this AB, it's supposed to be some arithmetic manifold that has an embedded hypersurface. So by hypersurface, I mean a codimension 1 submanifold that cuts it in half. And on the right, I have a different arithmetic manifold, which has two sides, say C and D, with the same exact, or at least an isometric copy of this hypersurface sitting inside it. And what you can do is you can cut the first manifold open on it and cut the second manifold open on this hypersurface. You can take the left half and glue it to the right half. And it turns out that if you do this in the right way, you'll get a finite volume hyperbolic manifold that's not commensurable to one of these arithmetic ones. So in particular, these are the first examples of non-arithmetic manifolds that worked in arbitrary dimension. And this cut and paste technique is originally due to Gromov, Piasecki, Shapiro. I guess there's a P missing on my slide. But it's been sort of subsequently generalized by various people after that. Okay, so let me talk a little bit about geodesic submanifolds of hyperbolic manifolds. So the following fact is a true fact that's about sort of negative curvature, which is that if you want to look at all the closed geodesics on your sort of favorite hyperbolic manifold, there's a lot of them. In fact, they're very, very abundant. So if you take, any given point and, any given direction, you might not find a closed geodesic in that particular direction, but nearby there will always be. And in fact, if you think about the set of closed geodesics on a hyperbolic manifold, they're dense on that manifold. So what I'd like to talk about is the sort of higher dimensional analog of that. So the higher dimensional analog are totally geodesic submanifolds. So for me, a submanifold will always be dimension at least 2 in this talk. And so what you think about is you have your sort of universal cover, you have HN, and if you take a geodesic plane sitting inside of it, some smaller dimensional hyperbolic space, then downstairs what you want is that when you quotient by this lattice, so you get your manifold M after I quotient HN by it, what I want is I want some submanifold that's sitting inside there. Now it might not be embedded, but I want it to at least be sort of immersed and totally geodesic. Okay, so these are sort of sticking smaller dimensional hyperbolic manifolds inside bigger dimensional ones. And the fact here is that you don't actually expect these things to exist very often. Okay, so here's the question, is when do such totally geodesic submanifolds exist? So in dimension at least 2, when do I have some properly immersed geodesic submanifolds sitting inside of there? Okay, so as of about maybe 3 years ago, there wasn't all that much known. So the one thing that you can prove, and I'll show you how to prove this on the next slide, or at least I'll talk through why this is true, is that arithmetic manifolds, they have 0 totally geodesic submanifolds, or they have infinitely many. Okay, and then what about for sort of non-arithmetic manifolds? What was known? Well, in dimension 3, it was known by work of several different people, including but not limited to Alan Reed, that there are examples of non-arithmetic manifolds that have 0 submanifolds. And in dimension 3, this was about the end of the story. So you can always, sort of using these cut and paste techniques, you could always construct hyperbolic manifolds that had non-arithmetic ones that had as many geodesic submanifolds as you want, as long as you sort of cut and paste a bunch of things together. But it was basically impossible to prove that they were finite. Okay, now in higher dimensions, say n at least 4, all the known manifolds, all the manifolds that can possibly be constructed by any known techniques, they all have at least one totally geodesic hypersurface. So by that I mean codimension 1. But again, as of about 3 years ago, the story was the same, namely that it was known that they have, at least one hypersurface, but if you had a non-arithmetic manifold, you could never prove that there were only finitely many. Some work, maybe I'll just plug, that I did with David Fisher, Jean Lafont, and Matthew Stover, is that for every n, in every dimension at least 3, we produce an infinite family of manifolds with finitely many totally geodesic hypersurface. Well, it's not to say we produced them, but we could actually prove that they had only finitely many totally geodesic hypersurfaces. And they also had at least one. So the novelty here is that for 3 manifolds, you had lots of non-arithmetic manifolds where you could actually prove they had a totally geodesic surface, but it was it wasn't known how to prove that they had only finitely many. So in this work, we showed at least how to construct some, and these constructions are exactly the same ones as these Gromov, Piatetsky, Shapiro examples that I talked about. Okay, so again, let's sort of continue on this line of when do totally geodesic submanifolds exist. So I want to talk about this sort of arithmetic case a little bit. So for arithmetic manifolds, you have this thing called the Margulis dichotomy. And the Margulis dichotomy says that if I have an arithmetic lattice and I look at its commensurator, which is some subset of the isometries, then this thing is dense inside of the group of isometries. So this commensurator, it's all of the isometries such that if I conjugate my lattice by it, and then I intersect it back with the lattice again, this is finite index in both the lattice and the conjugate of the lattice. So said another way, all of these isometries are giving rise to finite sheeted covers. So when I conjugate my lattice and I intersect and I get something finite index, that means what I have is I have my manifold, I have another manifold here, which is the one by conjugating my lattice, and I have a finite cover that sits above it. And so this commensurator, it produces sort of an abundance of finite covers in between these two manifolds. And so the Margulis's theorem, it's part of his sort of superrigidity theorem, says that if I have an arithmetic lattice, in fact, it's an if and only if, then this commensurator is in fact dense in G. So here there's a really nice sort of geometric corollary of this, which says that if I have some arithmetic manifold, then it either has 0 or infinitely many totally geodesic submanifolds. And kind of the idea is that like as soon as I have one totally geodesic submanifold, that gives rise to um, some subgroup of pi1 of my manifold. And what I can use is I can use this commensurator to sort of act on my entire lattice, this pi1, and it'll start to move this totally geodesic submanifold around. And then using this denseness of the commensurator, you can sort of ask, or sorry, using the denseness of this commensurator, you can basically produce infinitely more totally geodesic submanifolds. And so sort of from this, the question is, you know, if I have this abundance of totally geodesic submanifolds, so in particular, if I have infinitely many totally geodesic submanifolds, is it true that my manifold is necessarily arithmetic? So this question is originally due, I think, to, I mean, it's been informally asked by Alan Reed and for probably a couple decades or so in sort of all dimensions, and it was put in print by Kurt McMullen in Dimension 3. So the question is if I have infinitely many totally geodesic submanifolds of codimension 1, is my manifold necessarily arithmetic? So this is a partial converse where you get rid of the 0 part, because it's known non-arithmetic manifolds can also have 0 submanifolds. But if I have this sort of abundance of totally geodesic submanifolds, must it have come from an arithmetic manifold? So I've been working on this question for a couple of years now, joint with Botter, Fisher, and Stover. Oh, right, so sorry. So the remark here is that you can also ask this, the codimension 1 submanifold condition is not strictly necessary. You can ask it for higher codimension, provided that you ask that the submanifolds are maximal. So maximal means that they're not sort of properly contained in something of lower codimension. Right, so it turns out that the answer to this question is yes. So this is a theorem of Botter, Fisher, Stover, and myself. And so I'd like to sort of talk a little bit about what goes into the proof of this kind of a theorem. And I'd also like to sort of point out that we can also prove the same sort of a theorem for complex hyperbolic manifolds. So again, if you just ask about totally geodesic submanifolds of dimension at least 2 in a complex hyperbolic manifold, we can prove it there. So before I talk a little bit about the proof, let me do a quick digression into superrigidity. So superrigidity is originally due to Margulis, and I want to talk about what is a superrigidity theorem, and you know, where is it true? So here's the setup. So I have some representation. Again, gamma is always my lattice. So think of this as pi1 of your manifold. And let's say you have some representation into some k-algebraic group. So this is just some algebraic group over a field. And there are some technical conditions that I'm going to require. If you don't know what they mean, don't worry about it too much. It's not super important for this talk. But I want it to be, let's say, connected, adjoint, and simple. Okay, and what should K be? Well, K should be a local field here of characteristic 0. So again, if you don't like that, all I mean is that I want it to be the real numbers, I want it to be the complex numbers, or I want it to be a p-adic field, so QP or some finite extension therein. So, you know, if all of these adjectives aren't super familiar to you, just think of this as being some sort of matrix group that's sitting inside of n by n matrices over one of these fields. So over the complex numbers, over the real numbers, or over QP, say. Okay, so now what this produces for me is I have my representation H into this H. So the K is just to sort of decorate what the field that I'm looking at is. But you also have an embedding of the lattice into the corresponding isometry group here. So I guess it's not written here, but I'm thinking of G as being the isometry group. So again, if you're looking at hyperbolic manifolds, this is just the isometries of hyperbolic space. So here I have this little triangle, but there's sort of no diagonal that goes upwards. And for a representation to be super rigid, it means that I can fill in this diagram. So it means that there's some extension from G to H that's continuous. Okay, so a priori, these representations shouldn't have anything to do with each other. But for when a representation is super rigid, it means that I have some commutative diagram here. And so the big theorem of Margulis is that if I have some higher rank lattice, so higher rank means that its associated symmetric space has isometric copies of R2 or higher, is one way to say it. So the big sort of seminal work of Margulis is to prove that higher rank lattices are super rigid. So if you have any representation that's set up in this sort of way, then I can always extend it to this continuous representation from the isometry group that my lattice is sitting inside into H, which is just some group satisfying these conditions. Now, there are two technical conditions that I haven't written up, so let me put them up. So you have to assume that A, the representation is Zariski dense, meaning that it's sitting in basically the smallest possible thing that it can. And B, you have to assume that the representation is unbounded. So Q, P, R, and C, they all have norms on them. And you can therefore put a norm on the matrix group. And you want to know that you're unbounded with respect to this thing. Okay, but provided you're unbounded, you can always fill in this diagram. Okay, so here's an example. So take SLNZ for n at least 3. So this is a higher rank lattice, and you don't have to worry too much about what a higher rank lattice is. Just think about this group here. So the isometry group that it sits inside of is SL and R. And here, you could ask yourself, how do I classify all possible representations from a lattice into, let's say, PSL MR, where M is something, any sort of natural number. And again, let's throw these technical conditions on that is Zariski dense and unbounded. Well, Margulis tells you how to do this now. So superrigidity says that there's an extension from SLNR to PSLMR, and these sort of representations are much easier to extend, much easier to understand. So there's some sort of classical representation theory that tells you sort of how to do this. Okay, so let me just give you a quick sketch of the proof of superrigidity. So here's the setup again. I have some representation of my lattice into some group. And the step 1 in Margulis's proof is to build a boundary map. So you're going to build some measurable map that goes from G mod P, where P is a parabolic, to H mod Q, which is gamma equivariant. So I have gamma, which acts on the right on the right side of G here, and I have my representation, which gives me a way. Since it's a representation into H, I have a way to act on H mod Q, because H acts on H mod Q, so I can act via this representation. So I have some map here that's measurable, and it's gamma equivariant. So why is this called a boundary map? Well, it turns out that when you quotient by the right parabolic, this thing on the left here is the boundary of X, where X is the associated symmetric space. So to be super concrete, let's go back to our example here. So here I have G, which is the isometry group of hyperbolic space, and G mod P is nothing more than the sphere, which is the boundary of hyperbolic space. So my little cartoon here is that H3 is hyperbolic 3 space, and S2 is its sphere boundary. Okay, so this is literally a map out of the boundary of the symmetric space. So this is some measurable map that goes from this, and which is gamma equivariant. So that's why it's called the boundary map. Okay, so step 2 is, so this is an a priori measurable map, but it turns out that you can prove that this is actually an algebraic map. So it's rational in the sense of algebraic geometry. So this is a huge leap in regularity. So measurable maps, there's no reason to believe they have anything to do with algebraic maps, so maps cut out by polynomials or ratios thereof. But it turns out that this is, in fact, what Margulis proves. And the reason that this is important is it turns out that you can take, in sort of G cross H, you can take the graph of this representation and you can Zariski close it. And once you prove that this boundary map is algebraic, it allows you to prove that, in fact, this graph here is really the graph of a homomorphism. So what I can do is I can take the inverse projection on the first factor and then map via the second projection onto H, and it turns out that this is, in fact, a homomorphism. So the fact that this boundary map is algebraic has everything to do with this. And I want to point out that this sort of proving that this map is algebraic has everything to do with this higher rank assumption, which, by the way, hyperbolic manifolds don't satisfy. So hyperbolic manifolds are not higher rank, or hyperbolic lattices are not higher rank lattices. Okay, there's also an alternate take on this step too, due to Botter and Furman, which is that you can also, instead of deducing that this map is algebraic, you can instead use this boundary map to deduce that you have a measurable map from G to H, which is G cross gamma equivariant. So, from this, you can actually produce a continuous extension as well. Okay, so again, yeah, and I should point out, again, you critically need higher rank in this case. Okay, so how does one deduce arithmeticity from superrigidity? Well, let me just remind you of the theorem of Margulis. So it says that if I have a higher rank lattice, then any representation as above is in fact super rigid. And here's an informal definition. Oh, sorry. And the corollary is that if gamma is higher rank, then gamma is arithmetic. So again, this is due to Margulis. And so here's a really sort of definition that I wish I had more time to explain, but I don't. So one way to define arithmeticity is that associated to any lattice, there's a sort of very natural family of representations that you can sort of extract. And one way to sort of say that a lattice is arithmetic is that the image under this very natural family of, under every representation of this very natural family is in fact bounded. Okay, so I don't have time to explain this in full generality, but let me just give you an example. So again, let's revisit our friend SLNZ, which is a very nice arithmetic lattice inside of SLNR. Well, SLNZ, it also lives inside SLNQ because, you know, integral matrices are inside of rational matrices. And Q as a field, it lives inside of QP. Okay, so I can in fact map this SLNZ into SLN of, you know, sorry, I can map SLNZ into SLN QP. So this gives me a representation for each prime P of gamma interior. So this is a Zariski dense representation. Similarly, of course, to complete our triangle, you have a map into SLNR. That's just the sort of standard inclusion from the geometric structure. And so if you want to see that gamma is arithmetic, you want to see that so these are some of the natural representations and you want to see that they're bounded. So, okay, you can prove this by hand in this very special example, but let's just see how it follows from superrigidity. So let's assume that this representation is unbounded. Okay, so if it's unbounded, then Margulis tells you have this continuous extension. Okay, so in particular, I have an extension and I get a continuous map, a homomorphism from SLNR into SLNQP. And it turns out that the existence of such a representation tells you that you actually have a field embedding of R inside of QP. That's continuous with respect to the topologies on either side. But this is impossible because QP is, with its like p-adic metric, is actually a totally disconnected space. And so I'm mapping the real numbers with a continuous map into a totally disconnected space. Well, there's not that many maps that can do that. In particular, there's definitely no injections. Okay, so here's the contradiction. And so, you know, what assumption are we contradicting? We're contradicting the fact that this was an unbounded representation. Okay, so this is, and you know, if you can repeat this argument in full generality, essentially superrigidity tells you that anytime these things are unbounded, you get an extension, but then you have some issues with certain field embeddings, so you'll get contradictions. Okay, so let me talk a little bit about the ideas of the proof in like the last 5 minutes of how we prove that if I have infinitely many totally geodesic surfaces or hypersurfaces, then, so for 3 manifolds of surfaces, hypersurfaces in general, then my manifold's arithmetic. Okay, so again, here's the setup. I have my hyperbolic manifold, finite volume, has infinitely many totally geodesic hypersurfaces. I'll just do it in this case. So you can do it for maximal totally geodesic submanifolds as well. And what we do is, instead of looking at this boundary map, so the boundary map in Margulis's proof, you can always produce a boundary map, even in the hyperbolic case. So that's not the part where you need higher rank. But we take a slightly different perspective. Oh, sorry, I got ahead of myself. Right, so our goal is to prove a superrigidity statement. So of course, from what I sort of said on the last slide, that will tell us that this is arithmetic. And here, there are very specific representations that we're looking at here. So Margulis can prove it for all possible representations, as long as they fit the sort of technical adjectives I said before. But we want it for very, very specific ones. Okay, so instead of producing the boundary map, we produce a slightly different map. Okay, so you use the infinitely many totally geodesic, this should say hypersurfaces, to produce a map from G mod W into H mod something, where here G is the isometry group of hyperbolic space, and W, at least in the hypersurface case, is the isometry group of one less dimensional hyperbolic space. So what is this G mod W? It's not the boundary before. The boundary is G mod a parabolic. here instead what it is it's this is the sort of space of hyperbolic codimension 1 planes inside of hyperbolic space. So let me just give you a little cartoon here for H3. So I have H3, which is acted on by the isometry group of hyperbolic 3 space. Here's a geodesic plane that's sitting inside of it, this red one, and the stabilizer of that geodesic plane is a copy of, maybe up to some finite mess, is a copy of hyperbolic space of 1 dimension less. So one way to say this is that it's the space of all geodesic planes inside of hyperbolic space. And another way to say it, if you like the boundary better, so instead of thinking about the boundary, we're not thinking about that anymore. We're thinking about, in the case of H3, for instance, we're thinking about all of the circles on the boundary. So G mod W gives you all of the sort of circles on the boundary of hyperbolic 3 space. Okay, so it's a slightly different map, but what we prove is that you can produce, using these infinitely many totally geodesic hypersurfaces, you can produce this measurable map that's gamma equivariant out of this sort of different space. And so this one, you can't always produce. So the boundary map you can produce for any lattice. Choose your favorite one. But this one is a very special one. Okay, and then step 2 is to use this sort of Botter-Fuhrman technology to deduce, in fact, that you get a map from G to H, which is G cross gamma equivariant. So here G is acting on the left, gamma is acting on the right of G. And again, you have this, right, so I should point out that this critically uses the fact that you're looking at isometries of hyperbolic n space. So it critically uses something about the structure theory of G. In particular, it uses some very specific properties of its subgroups. And it also uses critically the H that we're looking at as well. So we're looking at very specific representations where we can actually understand which H we're looking at. But again, using this technology, Botter and Fuhrman tell you that there's a continuous extension. So in particular, you get this super rigid representation. Okay, so I promised a word about complex hyperbolic space. So if you allow me 1 extra minute, let me just talk about, so this works in real hyperbolic space, and this is how you deduce that it's arithmetic. In complex hyperbolic space, so now I have Hn, but the complex version, mod gamma. So gamma is a lattice in the isometry group of hyperbolic n space, which is SUN1, if this isn't a group you've ever sort of played around with. And again, we can prove this step 1, which says that there's this map which isn't out of the boundary, but out of this other space, which is gamma equivariant and measurable. So step 1, as before in our previous proof, it goes through exactly as before. But now it turns out that there are some bad representations. So there exist representations where this step 2 isn't possible. We can classify exactly which representations they are. They always land in a target SUN1. But unfortunately, there's just no way to give a sort of unified step 2, just like in the real hyperbolic case. So instead, what we prove in sort of a forthcoming paper is that I can instead deduce from this a measurable boundary map from the boundary of complex hyperbolic space to the boundary of complex hyperbolic space, which preserves some kind of incidence geometry. So if I'm going to be extremely sort of specific, what it does is if you take any 3 points which lie on the boundary of a complex geodesic, it can map it into 3 points on the boundary of a complex geodesic in the sort of target space. So somehow there's these are usually called chains. So somehow it's preserving the chain geometry of this complex hyperbolic boundary. And well, anytime you have such a map, it's actually a theorem due to Posetti that the existence of this map, in fact, gives you super rigid representations. So this is maybe, so this is a particularly nice theorem and a nice paper due to Posetti. In fact, she proves this in much more generality. But it turns out that anytime you have this sort of map between the boundaries of these, it in fact allows you to extend the representation. Okay, so we have some bad representations that we can't handle via our old step 2. But fortunately, as long as you prove that you can produce such a boundary map, then Posetti tells you that in fact you get the extension anyways. Okay, so I already went over time, so maybe I'll stop here. And if you have any questions, please feel free to come talk to me in office hours. And thank you.